Okay, so then last issue for today. Let's go back to, this is the question I posed to you guys on the first day of class. Started talking about limits. So now we can start to look at, we already looked at Lorentz contraction. What happens to the relativistic mass of an object as it approaches the speed of light? Okay, so again, this is, if we could probably write this as, instead, as a function. A little bit better to do that. So what are the constants in that expression? C and this quantity m naught, which is the object's rest mass. So at rest, that's the, if you went over to Mr. Cooper's lab and you measured the mass of this function, or of this object, that's what the scale would read. Okay, what the balance would read. So what's the variable? V, velocity, right? Because that's what we're varying here. So the relativistic mass as a function of velocity is this function. Okay, so then what's the limit of the relativistic mass as V approaches C? From which direction, by the way? Yeah, because we have to approach, we're starting from rest presumably, right? And we're accelerating to larger and larger velocities approaching C from values of V less than C. So it'd be C minus. Okay. So we get the limit of m naught divided by the square root of 1 minus v squared over c squared as v approaches c from the left. And what's that going to give us? That's going to give us something like the rest mass is just going to be some positive number, right? Don't know what it is, don't need to know. Divided by the square root of 1 minus, now what is this fraction going to become? I'm getting c minus squared divided by c squared. Yeah, what's that going to be? It's going to look like c minus over c. We could do that. We could square the what's that going to give us? C minus divided by c is going to be what? A number slightly less than the speed of light divided by the speed of light is going to be what? Slightly less than 1. Agreed? Everybody get that? The numerator is going to be just slightly smaller than the denominator, which means the quotient is going to be slightly less than 1, right? So we could rewrite that as m naught divided by the square root of 1 minus squared, a number slightly smaller than 1 squared is slightly smaller than 1, isn't it? 1 minus 1 minus. What is 1 minus a number slightly less than 1? 0 plus. What's the square root of 0 plus? Everybody agree? Square root of a very small positive number is a very small positive number. So what's that? What's a positive constant divided by a vanishingly small positive number? Infinity. There's your answer. That's why the speed of light is, it's not just a good idea, it's the law, right? It's the law of physics that no object with mass could ever possibly go the speed of light, because to do so would drive its mass up to infinity, which would require infinite energy, which the universe cannot supply, right? So what? So, okay, so this is what's bizarre about that. So does light have mass then? Light has no rest mass. It can't have any rest mass, or light couldn't go the speed of light, right? Light does have momentum, though. Ooh, that's weird. Remind me about that one. So we'll talk about that some Friday. Well,